Now, we've spent so much time talking about covalent compounds and how they interact through intermolecular forces that it's appropriate for us at this point to turn our attention to ionic substances and what's going on there. So we're going to explore ionic substances and how they interact. We're going to be able to use Coulomb's law to explain relative differences in lattice energies. And of course, that means we've got to know what a lattice is and be able to distinguish a lattice, an ionic lattice, from how molecules interact covalently, but then also how covalent network solids exist. So we're going to be comparing a variety of types of bonding in this lesson. All right, so let's look at ionic substances like sodium chloride versus HCl, which is believed to be covalent. But, examples of covalent substances, CO2, methanol, things like that. Anything that has primarily nonmetals in it. Well, remember, just a reminder that from CP we refer to any salt compounds or ionic compounds as salts, and of course any covalent compounds as molecules. And the term compound can be more appropriately used to really describe either of those two. Well, molecules exist as discrete compounds, as in individual compounds that interact through intermolecular forces. That's true of all types of molecular compounds. For instance, you can't see it because of me, but like H2S is a good example. They're discrete individual compounds that interact through intermolecular forces. Methanol is a good example, right? We imagine them as individual sort of satellites and they just sort of approach each other. But that's not true of sodium chloride and all ionic substances. Potassium carbonate, cesium bromide, anything that's ionic is going to interact through a series of positive and negative ions that is a lattice. So when we say something is, for instance, if I were to say something is like calcium bromide, this is not a discrete compound. We're just saying that in this sort of matrix that's being made, that there are two bromines for every calcium ion. It's just giving a ratio of the two ions, but they never exist individually like they do over with covalent compounds. And that's really fundamentally different. So you can imagine that we're not going to be talking about intermolecular forces in that way because they're sort of stuck together a lot tighter than that. There are a lot of different examples of these sort of matrices. You can see this one's meant to represent cesium chloride. This one down here is zinc sulfide. All ionic substances exist in a matrix that just sort of represents the ratio of ions. There's a lot more to this. As a matter of fact, if you look in certain AP review guides, like 5 Steps to a 5, they will talk a lot about face-centered cubic types of structures or body-centered cubic types of structures. And I'm telling you, this is not something that is pursued on the AP exam. You don't need to worry about that. All you need to know is that there are these sort of endless array of ions. They're not discrete molecules the way covalent substances are. Okay, so if you accept that idea and that we're going to refer to this as a matrix or a lattice, then we might start to wonder, well, how strongly are these, sodium and chloride ions held together? We get the feeling that intermolecular forces aren't very strong in covalent compounds, not nearly as strong as like a covalent bond. Would you expect like zinc sulfide or cesium chloride, would it be harder to split those ions than it would be, say, to split sodium chloride ions? And that idea is what we call lattice energy. So lattice energy is the amount of energy it takes to break apart the ions in a lattice. So that's very important. It's the energy it takes you to break that apart. And that amount of energy is much, much, much stronger than it is for covalent intermolecular forces. Like look over here, you can see we know London dispersion forces are the weakest. We'll compare their sort of less than 30 kilojoules. Look at hydrogen bonding can get up to 40 kilojoules. A little bit of foreshadowing. We haven't learned about ion dipole yet. We'll get to that. But hydrogen bonding is the strongest covalent intermolecular force that we know of, and it maxes out at 40 kilojoules. Whereas look at the lattice energy. If you have sodium chloride, right? It's 787 kilojoules per mole. That's a lot of energy it would take to break it apart. And I think that makes sense because salts have very, very, very high melting points, right? I mean, think about water boils at 100 degrees Celsius. You can really separate those water molecules, but take some table salt and put it in a pan and turn your burner all the way up. and nothing will happen. They have very, very, very high melting points because these attractions between these ions are much stronger. And I think that makes a lot of sense because we're not talking about partial positive and negative charges like we were with covalent substances in polar compounds. We're talking full-blown charges here, so you would expect those attractions to be a lot stronger. And for that reason, all ionic substances are solids at room temperature and pressure. So we're not going to see these discrete molecules in the way we are with covalent compounds. We're not going to see partially positives and negatives, and because of that, those interactions are going to be way stronger. As a matter of fact, if you were to compare it, we know that covalent bonds, actual carbon-oxygen bonds, is 358 kilojoules per mole, much stronger than a covalent intermolecular force. But notice they're not as strong as those lattice energies in ionic substances. Even actual covalent bonds typically are not as strong as the lattice energy in an ionic lattice. So what causes a certain combination of positive and negative charges to have more lattice energy or less? Well, you can see what's going on here. Like as we go from lithium fluoride to lithium chloride to lithium bromide, for some reason that lattice energy is going down. And all of a sudden as we get down here, look at how high these lattice energies are. Well, it's pretty easy to predict why this is occurring. The strength of a lattice depends on two factors. The charge of the ions. So for instance, I think it makes sense, right? If you go from a +1 charge to a +2 charge, look at how much higher the lattice energy is if you have +2 charges. As a matter of fact, if you have a +2 charge and a +2 charge, a negative or -2 charge, that's even higher. So the more you ratchet up the charges, the stronger the lattice is going to be. Look at aluminum 3+ down here. Whew, it's pretty high, right? Look at aluminum 3+ and oxygen 2-. Whoa, it's a lot of kilojoules. But the other thing is the atomic radius. Like, do you see how lithium is bonding with negative halogens, but yet that lattice energy is decreasing over time? So the atomic radius has a lot to do with it too. So let's explore why that is. Well, the way we describe the strength of forces in a lattice is through Coulomb's law. Coulomb's law is talking about the force of attraction or repulsion between two charges. Q1 is one of the charges. Maybe it's lithium plus. Q2 is another one of the charges. Maybe it's fluorine minus. Well, and R there is the distance between them. So, for instance, if we're talking about positives and negatives, here would be a good example, right? R is the difference between the distance between the nuclei of those ions. And we'd be talking, if we calculated, using Coulomb's law, if we calculated that force, it would be the force of attraction between those oppositely charged ions. If you had two similarly charged ions, which obviously we wouldn't be talking about a compound, but you could imagine if you were talking about like two electrons, both negative, you'd be talking about calculating the force of repulsion between those two. Now you can see I've got Coulomb's law constant up here. And that is going to imply that you're going to need to use Coulomb's law to calculate the force of attraction or repulsion. But that's never going to be true. I've never seen that on an AP test. You don't need to calculate it, but it's super useful for explaining some things. Like for instance, we said if we go from a +1 charge to a +2 charge, we should see an increase in the lattice energy. And the reason is because the force of attraction between those two, if I were to swap out one of the +1 charges here and change it to a +2, or I'm sorry, -1. If I were to swap out one of the +1 charges and switch it to a +2, you would expect that the force of attraction between those two would be a lot higher. And you can see it here because what you're doing is you're increasing the charge of the +1, say this is the negative and that's the positive. You would expect the force of attraction to get stronger. Now let's think about the distance between them though. Now the distance between them is greatly impacted by their radius. You can imagine if the chloride ion was something smaller, like say a fluoride ion is a little bit smaller, it'd be say this big, that's going to allow those two ions to get closer together. And then the distance between them will become smaller. So smaller ions can cozy up closer together. and you'll have a decrease in the distance between their radius, and that will cause a huge increase in the force of attraction. And you see that squared there? That's implying that a shrinking of the radius would have a much bigger impact than simply doubling the charge. And you can see that in a lot of these. Iodine is the largest of the ions. And because of that, it has to be it's the center of its nucleus has to be very far away from lithium, and so you get a pretty small lattice energy. Now, if you don't remember the size of the ions, let me show you this. We'll get back to that in a second. Remember that atoms and ions get smaller as you go up the chart, whoa, and smaller as you go this way. The smallest ions are over here. Now, I know there's a little bit of jump here at the negative ions, but even those, look within them. The negative ions get smaller as you go to the right. Helium is the smallest atom on the periodic table. Cesium is the largest in the main part of the periodic table. So as you go up and you go over, everything gets smaller. And as those ions get smaller, they have a lot stronger attraction because they're closer to the radius of the next ion. Now, one last thing you saw me bring up here is this attraction between charges is referred to as an electrostatic attraction. You want to avoid referring to this as a magnetic attraction. It's not magnetic. It's not gravitational, right? Don't refer to positive and negatives being attracted in that way. It's an electrostatic attraction. You can just use the word attraction, but don't call it a magnet and don't call it gravitational. Okay, so let's try this out. Based on what you just learned there, those two factors that impact it, the size of the charge and the radius, which of those two, calcium fluoride or barium fluoride, would you expect to have stronger lattice energy? Well, based on the two compounds, you can see that this is a +2 charge, and that's a -1 charge. Barium is right there. It also has a +2 charge, and that's a -1 charge. So the size of the charge, Q, is constant. We're not changing that. But if you were to look at these two atoms, you would expect, well, let's say here's a fluoride ion, there's a fluoride ion, and we have calcium, right? As you go down the chart, things get bigger. So calcium would be sort of like that size, and barium would be significantly larger. And because of that, the calcium is going to be able to scooch over and have a smaller distance between the two, and that smaller distance will cause a greater force of attraction. So I'd expect, because both ions or calcium is a smaller ion than barium, that calcium fluoride would have a stronger lattice energy. Let's try another one. Which salt would have a higher lattice energy? Calcium carbonate or potassium carbonate? Well, this one I don't think is going to come down so much to the radius. It could, but if we were looking at this and we were trying to figure out the radius, okay, I'm back. We were cooking and we set off the fire alarm. All right, so in any case, if you look at the charges of these two, potassium is +1, carbonate is -2, potassium is +2, carbonate is -2. So there is a difference in charge, and if I were looking at these two, I'd say definitely a +2 and a -2 would be more attractive than just a +1. So I'm going to say that one. Now, if you're looking at this and you're thinking to yourself, well, let me show you something. All right, so if you were looking at this and you were thinking to yourself, hey, what about the radius thing? Is it ever going to compete? Well, looking at this example, you can see that we decided based on there being a higher charge that it was going to have a higher lattice energy. But calcium's also a smaller ion, so you would expect it to be able to get closer to the carbonate ion, and therefore you would get a stronger attraction anyway. Can the two trends compete with each other? Absolutely, depending on the ions you choose. And remember, because the distance is squared, if you ever had to choose between an increasing charge and a increasing radius, say, the radius is going to have a stronger impact, all things equal. So that's how you figure out if one ionic substance has a higher lattice energy than another. All right, so you might start to wonder, okay, I get this. Positives and negatives can form a lattice in the way that salt did. Can nonmetals ever do that? Like, say for instance, could carbon and oxygen, carbon and oxygen typically form CO2, but those are discrete molecules, right? CO2 gases are separate from each other with an intermolecular force. But it turns out, yes, covalent substances like carbon and nitrogen and others can form regular arrays. Diamond is a good example. Each one of these gray balls here is a carbon, and it forms a regular array that's quite strong. And that's referred to, when that occurs, as a network covalent solid. They're not nearly as common as molecular compounds, discrete molecules, but they do happen. Graphite, pencil lead, is another one. It forms these nice little six-membered rings, and these are all carbon atoms that make some sort of a matrix a bit like a salt does. There are other examples too. But all of these are non-discrete molecule ones like we've seen before. So other examples, glass is an example. Silicon dioxide, window glass is an example of a covalent network solid. It's not silicon SiO2 separate molecules in the way you would see for a lot of covalent compounds. That's not how it works. It makes these regular arrays of silicons and oxygens that make kind of like a lattice, like ionic substances do. They're not discrete molecules. Silicon carbide is another example. But you notice these are pretty limited examples. They're not very common. Most molecules, most covalent nonmetals will form individual compounds that interact through intermolecular forces. It's pretty rare that you get a network covalent solid where you have nonmetals that make a matrix in the way that salts do.